Can we see a single particle of light? We see light every day. The sunlight entering through a window in the morning is light. The glow from a smartphone screen is light. And the stars in the night sky also tell us that they exist through light. But what would happen if we kept making that light weaker and weaker? Cut it in half, then in half again, and again. Eventually, we would reach a point where light could no longer be divided continuously, because light has a smallest quantum unit. We call it a photon. And that leads us to a fascinating question. If just one photon arrived, could we detect it? That is where today's story begins. An ordinary camera is not really designed to see one photon at a time. Even in a single pixel of a smartphone camera, many photons usually arrive. Those photons generate electric charges inside a semiconductor, and the accumulated signal becomes the brightness value of that pixel. Our eyes work in a similar way. But in modern science, there are situations where one photon matters. In quantum cryptography, information can be carried by individual photons. In photonic quantum computing, a single photon can play the role of a qubit. And when astronomers try to observe extremely faint light coming from unimaginably distant regions of the universe, missing just a few photons can change what can be measured. Imagine optical communication from deep space. A spacecraft sends a laser signal toward Earth from hundreds of millions of kilometers away. The transmitter may emit a strong beam, but after traveling that enormous distance, only a tiny fraction of those photons reach a small detector on Earth. In that situation, the important question is no longer, how bright is the light? It becomes, did a photon arrive or did it not? Modern quantum technology needs an answer to that question, and one of the most remarkable devices developed for that purpose is the SNSPD. The full name is Superconducting Nanowire Single-Photon Detector. It sounds complicated, but the physical idea behind it is surprisingly elegant. To understand an SNSPD, imagine an extremely narrow superconducting road. When a superconductor is cooled below a certain temperature, its electrons enter a very unusual collective state. Instead of behaving entirely as independent particles, electrons form correlated pairs known as Cooper pairs. Together, they create a macroscopic quantum state. An electrical current can flow without ordinary electrical resistance. Now imagine forming that superconductor into a wire only tens of nanometers wide. Then we send a current through it, very close to the maximum current that the superconducting state can tolerate. It is a little like filling a reservoir almost to the top of a dam. The system is still stable, but only just. Now one photon arrives. That photon carries only a tiny amount of energy. In an ordinary piece of metal, it might seem insignificant, but in an ultra-thin superconducting nanowire already operating close to its critical state, that tiny amount of energy can be enough. The absorbed photon disrupts some of the Cooper pairs and produces a very small region where superconductivity is locally suppressed. This region is often called a hotspot. It does not mean that the wire becomes hot in the everyday sense. It simply means that this microscopic region has received enough energy to behave differently from the surrounding superconducting material. You can think of it as an obstacle suddenly appearing in the middle of our narrow superconducting road. The electric current is forced into the remaining available path. The local current density rises, and eventually superconductivity can no longer be maintained. For a brief moment, electrical resistance appears. That produces a short voltage pulse. Electronic circuits amplify that pulse, and we can say, a photon just arrived. Think about what has happened. We did not literally see the photon itself. We detected the disturbance that a single photon created in a collective quantum state. For a single photon detector to be useful, however, sensitivity alone is not enough. There are several crucial performance measures. The first is detection efficiency. If 100 photons reach the detector, but only 20 are registered, the detector is not particularly useful. The second is the dark count rate. A dark count occurs when the detector produces a signal even though no photon has arrived. Imagine a doorbell that rings when nobody is at the door. No matter how sensitive that doorbell is, it would soon become useless. The third measure is timing jitter. This tells us how accurately the detector can determine the arrival time of a photon. And the fourth is recovery time. After detecting one photon, how quickly can the device return to its original superconducting state and become ready to detect the next one? Modern SNSPDs have achieved extraordinary performance across these metrics. That is why they are becoming important in quantum communication, quantum computing, astronomy, precision spectroscopy, and LiDAR. For many years, SNSPD technology has been developed mainly using superconductors such as niobium nitride, NbN, and niobium titanium nitride, NbTIN. These materials are fast. They can provide excellent timing performance and robust superconducting properties. Later, amorphous superconductors such as WSi and MoSi attracted attention. These materials offered advantages for detecting lower energy photons. And gradually, researchers began looking toward longer and longer wavelengths. Why? Because wavelength and photon energy are connected. The longer the wavelength becomes, the smaller the energy carried by each photon. An infrared photon carries less energy than a visible photon, and photons in the terahertz region carry even less energy. So the challenge of long-wavelength single-photon detection is fundamentally this. How small an energy quantum can we still recognize as an individual event? And that is where a new material enters the story. Niobium diselenide, NbSe₂. NbSe₂ is a fascinating material. Like graphene, it belongs to the family of layered, two-dimensional materials. Its atomic layers are held together relatively weakly, which means the material can be made extremely thin, down to only a few atomic layers. But unlike graphene, NbSe₂ becomes a superconductor at sufficiently low temperatures. A monolayer is only about 0.7 nanometers thick, that is far thinner than a human hair, by roughly 5 orders of magnitude. Why does being so thin matter? Imagine delivering the same small amount of heat to a massive steel plate and to an extremely thin piece of material. The large plate barely changes. The smaller object responds much more strongly. Something analogous can happen in a photon detector. If the tiny energy carried by a photon is distributed through a large superconducting volume, its effect may be too small. But if that energy is deposited into a superconducting structure only a few atomic layers thick, the local disturbance can become much more significant. This is the possibility explored in a recent Nature Communications study. The researchers protected few-layer NbSe₂ with another two-dimensional material called NbN and patterned it into superconducting nanowires only about 60 to 100 nanometers wide. A representative device contained only about 7 layers of NbSe₂. Remarkably, the superconducting properties survived the fabrication process quite well. The superconducting transition temperature remained around 6 Kelvin. Then the researchers illuminated the tiny nanowires with light, first at 780 nanometers and then at 1550 nanometers. The second wavelength is particularly important because 1550 nanometers lies at the heart of modern fiber optic communication and quantum communication. But there is an important question. Just because a detector produces an electrical signal, how do we know that the signal was truly caused by one photon? The researchers used a clever method. They changed the laser power and measured how the count rate responded. If one photon is sufficient to trigger one detection event, then doubling the average photon flux should approximately double the number of detected events. But if 2 photons are required simultaneously to produce a detection event, the dependence becomes different. And this is exactly what the researchers investigated. At 780 nanometers, the count rate increased linearly with optical power over a broad range. That is strong evidence that individual photons were producing individual detection events. The result at 1550 nanometers was even more interesting. At lower bias currents, the detector initially behaved as though 2 or 3 photons were sometimes needed. But as the superconducting nanowire was operated closer to its switching current, the response entered the single-photon regime. The linear dependence persisted across more than 3 orders of magnitude in optical power. In other words, the researchers demonstrated that a superconducting NbSe₂ nanowire only a few atomic layers thick can detect individual photons. The device also showed impressive basic performance. Its dark count rate remained below approximately 1 count per second, and its timing jitter was about 45 picoseconds. A picosecond is 1/1,000,000th of a second. In 45 picoseconds, light travels only about 1.3 centimeters. That gives us a sense of the timescale involved. Of course, the very best optimized SNSPDs in the world can achieve timing jitter of only a few picoseconds. So it would be wrong to say that this new NbSe₂ detector has already surpassed the best conventional SNSPDs. It has not. This device should be viewed as a proof of concept. There are still important challenges. One of them is called latching. After a photon is detected and a region of the wire becomes resistive, the detector should quickly cool down and recover its superconducting state. But electrical current can generate enough Joule heating to keep the device trapped in a resistive state. That limits how quickly and reliably it can operate. The researchers used a parallel resistor to reduce this problem. The device also did not yet show the saturated internal detection efficiency expected from a fully optimized SNSPD. So the major importance of this work is not that it produced the world's best single-photon detector. Its importance is that it demonstrated that this entirely new material platform actually works. And perhaps the most provocative figure in the paper is not the experimental data itself. It is the future projection. The researchers used a hotspot model to estimate how far the detection wavelength might be extended if NbSe₂ devices were optimized. Traditional NbN-based devices are ultimately challenged as the photon wavelength extends toward tens of micrometers. Materials such as WSi can push the sensitivity farther into the infrared. But according to the model used in this study, an optimized monolayer NbSe₂ device could, under favorable conditions, have a cutoff wavelength extending beyond 1 millimeter. 1 millimeter. That takes us deep toward the terahertz regime. Now, an important distinction must be made. The researchers did not detect a 1 millimeter wavelength single photon in this experiment. The actual demonstrations were performed at 780 and 1550 nanometers. The millimeter scale cutoff is a theoretical projection for future devices with much better geometry and operating conditions. Still, the possibility is intriguing, because if such detectors become practical, we would no longer simply be detecting longer wavelength light. We would be learning how to detect increasingly smaller packets of energy as individual quantum events. NbSe₂ has another important property. It is a two-dimensional material, and two-dimensional materials can be stacked almost like atomic-scale Lego blocks. NbSe₂ can be combined with graphene. It can be placed next to HBN. It can potentially be integrated with semiconductors, magnetic materials, and many other quantum materials. These structures are known as van der Waals heterostructures. And this opens another possibility. What if we place an atomically thin superconducting detector directly next to the quantum material we want to study? Until now, SNSPDs have mainly been used to detect photons arriving from the outside. But in a future heterostructure, perhaps the detector could respond to extremely small excitations generated inside neighboring quantum materials. Excitons, phonons, plasmons, spin excitations, perhaps even more exotic collective modes. The authors of this study also point toward the possibility of locally probing such low-energy excitations. If that becomes possible, the meaning of SNSPD may begin to change. It would no longer be merely a single-photon detector. It might evolve towards something closer to a single excitation detector, a device capable of registering individual quantum events inside matter itself. So where could this technology be used? The first obvious application is quantum communication. In quantum key distribution, individual photons can carry quantum information. That means detecting the photon is every bit as important as generating and transmitting it. Better single-photon detectors can improve communication distance, data rates, and overall system performance. The second application is photonic quantum computing. In many photonic quantum computers, the result of a computation is ultimately determined by detecting where photons arrive. Even the most sophisticated quantum circuit is of little use if the photons at the output cannot be detected efficiently. The third application is space communication. Imagine a spacecraft near Mars, or even farther away, sending data back to Earth using laser communication. As the distance grows, fewer and fewer photons reach the receiving telescope. In such a regime, every photon becomes valuable. The fourth is LiDAR. LiDAR measures distance by sending out laser pulses and detecting the returning light. If a detector can reliably work with only a handful of returning photons, it can potentially measure longer distances using lower optical power. The fifth application is astronomy. Some of the most interesting objects in the universe are also among the faintest. Very distant galaxies, weak signals associated with exoplanets, extremely subtle signatures from the early universe. In such observations, a single photon is not merely light, it is information. And if single photon detection can eventually be extended farther into the mid-infrared and terahertz regions, entirely new types of spectroscopy may become possible, probing molecular rotations, vibrations, and low-energy excitations in quantum materials. But how close is SNSPD technology to becoming an industry? It is easy to assume that technologies like this exist only inside university laboratories. That is no longer true. SNSPD systems are already commercially available. They are used by quantum communication companies, quantum computing laboratories, universities, national research institutes, and organizations working in advanced sensing, space, and defense technologies. But they are not yet mass-market devices like smartphone cameras. SNSPDs remain specialized high-performance instruments, and the largest reason is simple. They need to be cold. Superconductors only work below their critical temperatures. The NbSe₂ device in this experiment was operated at around 1 Kelvin, 1 Kelvin is roughly minus 272 degrees Celsius. Reaching and maintaining such temperatures requires sophisticated cryogenic equipment. That makes the system larger, more expensive, and more complex than ordinary semiconductor photodetectors. So the future of SNSPD technology will not be determined by the detector material alone. It requires progress in cryogenics, photonics, electronics, packaging, and integrated optical circuits. The industrial competition may therefore become less about building the best isolated detector and more about answering a larger engineering question. How small, inexpensive, reliable, and integrated can an entire cryogenic quantum detection system become? The future directions are relatively clear. First, higher detection efficiency. Second, lower dark count rates. Third, even smaller timing jitter. Fourth, shorter recovery times. Fifth, large detector arrays containing hundreds or thousands of pixels. And instead of placing detectors only at the end of optical fibers, researchers are working toward integrating them directly into silicon, photonic circuits, and other optical chips. Then there is another direction highlighted by this NbSe₂ work, detecting smaller and smaller energy quanta, from visible light to near-infrared to mid-infrared, and perhaps eventually to the terahertz regime. And if we continue along that path, we may eventually face an interesting question. Are we still building a light detector? Or are we building something more general? A detector of quantum events? At this point, let us move briefly beyond engineering and think about what it means to see. In everyday life, seeing means recognizing the appearance of something. We see a mountain. We see another person's face. We see a star. But in the quantum world, what we call seeing is different. An SNSPD does not take a photograph of a photon. Instead, it records the consequence of an interaction. One photon enters a superconductor. A tiny amount of energy is transferred. Some Cooper pairs are disrupted. A collective quantum state involving enormous numbers of electrons changes. And that microscopic disturbance becomes a macroscopic electrical pulse that we can record. A microscopic quantum event becomes a fact in our macroscopic world. In that sense, a single-photon detector sits very close to one of the oldest philosophical questions in quantum mechanics. How does possibility become an event? When does information become a fact? What exactly does it mean to observe something? An SNSPD does not solve the quantum measurement problem, but it gives us a remarkably tangible example of the boundary. On one side, a single quantum of light. On the other side, a classical electrical signal stored in a computer. And between them, a thin strip of superconducting matter. When we look back at the history of science, it often seems like a history of building bigger things. Larger telescopes, more powerful particle accelerators, faster computers, stronger rockets. But there is another history of science moving in exactly the opposite direction. It is the history of learning to distinguish smaller and smaller differences. Galileo's telescope revealed stars invisible to the naked eye. The microscope opened the world of cells. The electron microscope revealed atomic structures. Gravitational wave detectors learned to measure distortions of space far smaller than the diameter of a proton. And single-photon detectors register individual quantum events of light. Science has not advanced only by learning how to shake the world harder. It has also advanced by learning how to listen more carefully. Now imagine one final scene. Somewhere in a distant galaxy, a photon begins its journey. It travels for millions, perhaps billions of years. It crosses the darkness between stars. It passes through the vast emptiness between galaxies. Eventually, it arrives on Earth, and there it is absorbed by a superconducting material only a few atomic layers thick. For a brief moment, the quantum order inside that tiny object is disturbed. A voltage pulse appears. A point is registered on a computer. And we say, something arrived. An event that began billions of years ago in a distant part of the universe has become one piece of information inside a human-made nanostructure. I think that image captures something essential about modern science. We cannot control the entire universe. There are limits to the energy we can generate. There are limits to how far we can travel. But we are becoming extraordinarily good at listening. We see fainter light. We measure smaller vibrations. We detect increasingly tiny amounts of energy. This NbSe₂ work is still only an early step. It has not yet surpassed the best conventional SNSPDs. And it has not yet demonstrated terahertz single-photon detection. But the fact that a superconductor, only a few atomic layers thick, can detect a single photon opens an intriguing path forward. And if one day such detectors can sense not only individual photons, but also individual phonons, excitons, or tiny changes in spin, we may gain an entirely new kind of eye for the quantum world. Perhaps the most advanced technology of the future will not be the technology that moves the world with the greatest force. Perhaps it will be the technology capable of noticing the smallest change. The technology that hears not the universe shouting, but the universe whispering. And today, to hear one of those whispers, we are building superconductors only a few atoms thick. This has been ThothSaem's Science Catch.